Two players play the game using an ordinary deck of cards. The cards will be dealt out in a row, one after another. Before the dealing begins, each player claims an ordered sequence of colours that might turn up. For example, red, black, red, or black, red, red. As the cards are dealt, if 3 successive cards turn up in one of these sequences, the player who claimed it gets to collect those 3 cards as a trick, and the dealing continues. This sounds like a perfectly even game, but in fact the second player has a strategy that will give him a significant advantage. When the first player has chosen his sequence, say red, red, black, the second player changes the middle colour, adds it to the start of the sequence, discards the last colour, and claims the resulting sequence, in this case black, red, red. This gives a decided advantage to the second player no matter which sequence his opponent has chosen. When all 52 cards have been dealt, the player who has collected the most tricks wins. Let's see how this plays out. As you can see, player 2 won comfortably using this method, but how? To understand this, we need to look at a similar game labelled Penny's Game. This involves selecting a sequence of 3 flips, flipping the coin repeatedly and seeing whose sequence comes up first. Again, like the other game, the second player changes the middle flip, adds it to the start of the sequence, discards the last flip, and claims the resulting sequence. These are both non-transitive games. This is where various strategies produce one or more loops or preferences. In a non-transitive game, in which strategy A is preferred over strategy B, and strategy B is preferred over strategy C, strategy A is not necessarily preferred over strategy C. So if one player picks their choice of cards, player 2 could pick a choice of cards that is preferred over the first player's choice. Just like the game Rock, Paper, Scissors, there's no best play. The second player must choose their selection of cards based on the first player's choice. Now let's prove this by looking at Penny's Game. The following rules exist for player 2's selection, based on the selection made by player 1. Assume that player 1 chooses heads, heads, heads. In that case, the second call is for heads. Flip that selection to a tails and move it to the beginning of player 2's sequence. Next, take the first 2 calls in player 1's sequence and take those as the second and third call in player 2's. Doing so results in tails, heads, heads for player 2, a selection that will win most of the time against player 1. Player 1's third call is not considered. We will first calculate the probability that tails, heads, heads will appear before heads, heads, heads. Assume that player 1 selects heads, heads, heads. Should that sequence appear in the first 3 tosses, then player 1 will win. In any other situation, player 2 will win. The probability that the first 3 tosses will come up heads, heads, heads is a half to the power of 3, which is equal to 1 over 8. Thus, the probability of tails, heads, heads before heads, heads, heads is equal to 1 minus 1 over 8, which is equal to 7 over 8. Let us next calculate the probability that tails, heads, heads will appear before heads, heads, tails. The probability of flipping heads, heads, tails, or heads, 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 tails, or heads, 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 tails is equal to 1 over 4. This gives the probability of heads, heads, tails winning. The probability of tails, heads, heads winning is therefore the complementary event, and thus probability of tails, heads, heads before heads, heads, tails is equal to 1 minus 1 over 4, which is equal to 3 out of 4. Player 8's odds are therefore 3 out of 4. Computing these results for all possible 3 coin toss combinations, we get this table of probabilities. Using similar calculations, we can prove why this also works for the Humble-Nishiyama Randomness game.